All right, students, this is Mr. Shields, and let's go ahead and work a few problems from Chapter 20. So this is Chapter 20, okay, and we are on page 729 in the textbook. And of course, I've already sent you a list of problems at the beginning of the semester that I have assigned out of every chapter, okay. And so you already know what you need to be working on, okay? You already know that these problems I assigned at the beginning of the semester that I sent to you in an email and an announcement in Blackboard, that that's what I will build the quizzes from and the midterm and final exams from, okay? So you should already know this, okay? All right, so let's look at number 6, okay? So we're number 6 on page 729. So we have a glass rod that has been charged to positive 12 nanocoulombs. So we got a glass rod, okay? And it has been charged to 12 nanocoulombs of charge. And it touches a metal sphere, okay? So we got a metal sphere here. All right, and let's just draw the sphere right there. There's the metal. This is metal. This is glass, okay? Of course, you always need to draw everything and label it. And it touches a metal sphere, and afterward, the rod's charge is positive 8 nanocoulombs. So after it touches, the metal sphere, the charge is, and by the way, that's charge, the charge is positive 8 nanocoulombs, okay? All right, and so the question is, what kind, let's look at 6A. It says, what kind of charged particle was transferred between the rod and the sphere, and in which direction, okay? Well, in order for it to go from positive 12 to positive 8, and remember this is algebraically, you would have had to have added 4 nanocoulombs of negative charge to get it to positive 8, okay? And so what happens is these electrons would have gone towards the rod or went into the rod in order for it to go from positive 12 to positive 8. So we would have added negative 4 nanocoulombs of charge to the rod. And which direction would it have gone? It would have gone from the sphere to the rod, okay? That's pretty easy, okay? Then it says, part B, how many charged particles were transferred, all right? So 6B, how many charged particles were transferred? Well, we know that there were 4, and of course we'll keep it negative if you want to. It really doesn't matter to find out. We're just looking for the absolute value or the magnitude of charged particles, okay? We know it's electrons. We'll go ahead and keep it negative. So we know there were 4 nanocoulombs, which is 10 to the negative 9th. And we know that every charge, whether it's an electron or a proton, has that one electron or one proton has a value, and since it's electrons, we'll put a negative on that. 1.6 times 10 to the negative 19th coulombs, okay? All right? And that's coulombs per electron. That's coulombs per electron, okay? All right, now, so we want to find out now how many electrons were added. Well, we just divide. So we take what? We take 4 to the negative 9th, so we take 4 to the negative 9th and divide it by 1.6 to the negative 19th. And we come up with what? We come up with 2.5 times 10 to the 10th electrons, okay, were added. Or we could say 25 billion, Okay? You could say it that way. And so that's how we calculate that. It's real easy. Real easy, all right? All right, let's move on. Let's look now at number 14. Okay? Number 14, we'll go to a clean slide. So we'll go to number 14. A small plastic sphere with a charge of negative 5 nanocoulombs. So we got a small plastic sphere that has a charge of negative 5 nanocoulombs. Remember, nano is 10 to the negative 9th. Is near another small plastic sphere with a charge of negative 12. So you've got this one. I wished it wouldn't do that. I don't know why my pen acts like that. It's very irritating. Okay. All right. And so let's just put it right here, okay? And this one, and they're fairly close, is what? Negative 12 nanocoulombs of charge. So that one has a negative 12. If the spheres repel one another with a force of, and they will, okay? They'll repel each other. And they repel each other with a force of what? 8.2 to the negative 4th newtons. So 8.2 times 10 to the negative 4th newtons. What is the distance between the spheres? So we're looking for this right here. We're looking for this distance right here. That is called the radius. R can be radius or distance, okay? Or x. If you wanted to make it x, you could, or y, since I put them in the y-axis. You could do it that way. It doesn't matter. As long as it's a unit of displacement, okay? All right, which is in meters, all right? So we want to know what the distance is. Well, this is a Coulomb's law problem, all right? We know that Coulomb's law is that you take Coulomb's electrical constant times the absolute value of Q1 times the absolute value of Q2 divided by R squared, right? The inverse square law comes into effect here. Well, I say it does if the charges are like charges. It's still inverse square, but if the charges are not like charges, then the amount that the force is affected by will not be exactly 25% if you double it. So you have to be careful when we say that, okay? You have to be aware that that inverse square law only applies if the charges remain constant. They're both the same, which here they're not, and you double the distance. Then it's 25% of the original force. But that's not the case. They're not both the same, okay? All right, so now we want to solve for R squared, don't we? Well, okay, you do your algebra. So we say R then is equal to what? R, I've got it written down somewhere. Okay. Well, good heavens. I thought I had it written down somewhere. Yeah. So we say then we solve for R, and R becomes what? R becomes the square root of Coulomb's electrical constant times the absolute value of Q1 times the absolute value of Q2 divided by the force. And that's all under the radical, okay? Everything's under the radical. All right? Okay. So now let's substitute everything in. We got 9 times 10 to the 9th. I'm just going to go ahead and round it. Newtons, meters squared. Good heavens. I'm writing it backwards. I'm sorry. It's been a little while since I've done the Coulomb's law. It's newtons meters squared per coulomb squared. All right. Put that in parentheses. And then we have negative 5 nanocoulombs times negative 12 nanocoulombs all over 8.2 to the negative 4th newtons. Okay. And we should get an answer very close to this, that R is equal to what? 0.26 meters, 0.026 meters, right? Or you could say 2.6 centimeters. All right. Now again, that's close, okay? That's been rounded. All right. You may not get exactly that number, but that's been rounded, okay? All right, okay? All right, that's an easy problem. And of course, you do see everything cancels out but the meters. Okay? Everything cancels out but meters. All right. All right, where are we here? So that's number 14. All right, let's go on and look at a couple of more. Let's look at number 16. Let's go to a clean slide. So number 16. Now, if you notice, the end of the chapter, in the back of the book, in the appendix, are all the odd numbered answers to all the problems. However, too, now, let me say this. If you go to the study area in Blackboard, you will see that there are tutorial videos that you can watch, tutorial problem-solving videos, and they work several throughout each chapter. And sometimes they work even numbers, and sometimes it's odd numbers, or both. So be sure you look at those, and the people that do that for the text do a really good job. Okay. All right. So let's look at number 16. We got a small glass bead has been charged to positive 20 nanocoulombs. Okay. So we got a small glass bead, and it has been charged to positive 20 nanocoulombs. All right. All right. A tiny ball bearing 1 centimeter above the bead. So we got a little tiny ball bearing. I'll tell you what, let me erase this and lower it down a little bit because I'm about to get too high. All right, so we got a glass bead. So this is a glass bead. All right. And it has a charge of positive 20 nanocoulombs. And we got a little ball bearing up here. All right. And it is 1 centimeter. This distance right here is 1 centimeter. That's 1 centimeter, which is what? 0.01 meters. Yeah. Okay. Remember now, got to have everything in meters. Okay. Don't forget that. All right. And the force that it feels is a downward electrical force. So it's feeling a downward electrical force. Okay. The force is downward. And the force is what? It's real small, 0.018 newtons. Okay. All right, now I know I wrote that a little small, but again, you can see the force there. Let me make my F a little bigger. So the downward force is 0.018 newtons, okay, and it's downward. What is the charge on the ball bearing? Okay, well, this is another Coulomb's law. And again, we know that Coulomb's law says what? That we could take Coulomb's electrical constant. All right. And we can, by the way, there's a couple of different ways we can say this. We can say 1 over 4 pi epsilon naught, or just 9 times 10 to the 9th. And I like to go with 9 times 10 to the 9th because it's just easier to use in this application, okay? So I got the absolute value of charge 1 times the absolute value of charge 2 divided by r squared, okay? So it gave us, and by the way, this would be r. This, oh man, don't tell me I just erased it. Good, I didn't. That would be r. Okay, because that's the distance between the two objects. And we've got to solve now for what? We've got to solve for Q2. So we've got to solve for Q2. So let's work out our problem. And you always want to solve for the equation first and then do the math. Because now some people don't like to do that, but you really should, because that's the physics. Okay, that's the physics part. And then all you do is just plug in the numbers, and that's the math part. Okay, so if we solve for Q2, Q2 is equal to what? Well, let's see, that's going to be what? We're going to, that would be the force divided by Coulomb's electrical constant. Okay. All right. Times r squared. Okay. Let's make sure we don't mess nothing up now. All right. Times Q1. Times Q1. Okay. Now we've got our formula worked out, so now let's just plug everything in. So we've got 0.018 newtons times r squared, which is what? 0.01 meters squared, divided by 9 times 10 to the 9th newtons meters squared per coulomb squared, times what? Plus 20 nanocoulombs. Now, folks, you need to learn your prefixes. All right, so let's do the math. Let's make sure we've got everything set up right, because I boo-boo sometimes. We're going to try not to. So we got 0.018 times what? All right, 0.01 squared. And then we divide that by what? 9 to the 9th times what? 20 to the negative 9th. And we get 1 times 10 to the negative 8th coulombs. Yay! And that's what we're supposed to get. 1 times 10 to the negative 8th coulombs. Now we could go ahead and put that in nanocoulombs, and that would be how many nanocoulombs? That would be 10 nanocoulombs of charge. Okay, right? Which is equal to 10 nanocoulombs. You say, how do you know that? All right, now look, you're going more negative. You move it one more place to the right, and that becomes what? Negative 9, which would make it 10 nanocoulombs, okay? Now, does it ask about the charge? Let's see, what did it ask? Let's see, what is the charge on the ball bearing, okay? And of course, since it's downward, since it's attractive, it would have to be a negative, wouldn't it? You say, how'd you know that, Mr. Shields? Because it's attractive, okay? The glass bead is positive, so that means the ball bearing would have to be negative, okay? It's an attractive force, okay? Like, remember the law of charges. Like charges repel, and unlike charges attract. It's a very basic, very simple, basic law of electrical physics, the law of charges. And I need to always remember that, okay? So that's number 16. All right? Okay, now let's do one more. Number 33. So let's look at number 33. Oh, by the way, that was on page, this was on page 730. And this one is on page 730 also. Yeah. So that's on page 730. And this is on page 730, okay? All right. So we got a parallel plate capacitor is formed from two 4x4 centimeter electrodes. So I'm going to draw them vertical. So we got parallel plate capacitor here. We got one here. I'm just going to draw them vertical. That's supposed to be a little more symmetrical or a little more consistent with the other. I'm not the best drawer and artist in the world. All right, so they're 4x4 centimeter electrodes. Okay, so there's two of them. So we're just going to say that the plates are 4 centimeters by 4 centimeters, okay, each. Okay? All right, and they are spaced 2 millimeters apart. So the distance from here to here is 2 millimeters, which is what? 2 times 10 to the negative 3rd meters, correct? Okay. 2 millimeters, which is 2 times 10 to the negative 3rd meters. And so that's the distance, D. D is equal to distance. Or it could be R if you want to make it R. Okay. Or X, or whatever you want to make it. Again, it's just a unit of distance. That's the biggest thing to remember. Try not to get all wound up with what symbols we use. Just be sure that you know. And here again, this is knowing the physics, the conceptual part of it. Okay. Very important to remember that. Okay. Very, very important to remember that. All right. Okay. So if we look at our textbook, and I think it's equation 20.7, not sure what page that's on, we can find then the electrical field. We can find the electrical field in a capacitor by this equation right here. Q divided by epsilon naught times the area. We can find the electrical field, all right? But it wants to know what? it wants to know what is the charge in nanocoulombs on each electrode. Okay, so we want to know Q. Well, here again, let's solve for the equation first. So we're going to do what? Q then, we're going to multiply the electric field by what? Epsilon naught times the area. So the electric field times epsilon naught times the area will give us the charge on each plate. It's a very simple problem, very easy equation, okay? And so now let's plug everything in. Well, we need to go back and look at some more of our data here. All right, now what is this? Remember, y'all, we got to put everything in meters. So 4 centimeters is 0.04 meters by 0.04 meters. I hope you caught that. Okay, I don't need to remind you that every time we do these. Okay, you remember, y'all, 90% of the time in physics calculations, unless we're looking at thermal expansion, you know, everything has to be in meters. Okay, has to be in meters. Okay, all right, when we're looking at units of length. All right, okay, and what is epsilon naught, this constant? Epsilon naught, boy, that's a horrible epsilon, isn't it? Oh me, old Colonel Stamper would be disappointed in me. I can't make my symbols any better than that. That's a little better. And again, this is in your textbook. It is 8.85, so it's 8.85 times 10 to the negative 12th. And it's what? Coulomb squared per Newton, Coulomb squared per Newton, meter squared. Hey, that looks real familiar, doesn't it? Yeah, that's the reverse, or that's the reciprocal of Coulomb's electrical constant, isn't it? It's Newton's meter squared per Coulomb squared. Well, remember what I said earlier, that we could use 1 over 4 pi epsilon naught to as our electrical constant, okay? All right, well, anyway, here we go. All right, now, so there's your epsilon naught. So now let's plug everything in. So the charge is equal to what? The electric field. Oh, shoot, we didn't write the electric field, did we? I apologize. What was the electric field? The electric field was 1 times 10 to the 6 newtons per coulomb. I bet y'all were saying, what's the electric field? All right, well, it's 1 times 10 to the 6th newtons per coulomb. There we go. I got a little ahead of myself. Sorry about that. Now we can find the charge. So we have the electric field, we have epsilon naught, we have our dimensions in meters. Now we can find the charge, okay? So the electric field is 1 times 10 to the 6th newtons per coulomb times, all right, now look, we've got to do what next? Let's do epsilon naught and then area last, all right? 8.85 times 10 to the negative 12th, and that's Coulomb squared per Newton's meter squared, okay? And then we're going to do area, and I'm going to do a brackets, and so we're going to say, I don't guess I had to do brackets. Nah, we won't do brackets. We'll just do parentheses. Why did it do that? I clicked on the wrong thing. There we go. So we're going to say 0.04 meters times what? 0.04 meters. That's to find the area, because it was a rectangle, all right? And what's the area of a rectangle? Or a square, excuse me, not rectangle, square, because it was square. Well, it's length times the width, right? Okay. And that goes to the area for a rectangle or a square, okay? All right, so there's the area. And then we come up with a charge of what? We should get a charge of 14 nanocoulombs. 14 nanocoulombs, all right? And again, that's rounded. Let's see if it comes out to exactly that. All right, so let's see, it's 1 to the 6 times 8.85 exponent negative 12th times 0.04 times 0.04, and that's in parentheses, equals, yeah, I get 1 point, this is what I actually get. This is 1.416 times 10 to the negative 8th coulombs, and if you move it one place, and again, that's rounded, y'all, that would be 14.16 or just 14 nanocoulombs, right? 14.16 or just 14 nanocoulombs, all right? That's what we actually get. That's the actual calculator answer, all right? All right, so we get 14 nanocoulombs. All right, now, what should we remember about this, okay? All right, well, first of all, we need to realize that one plate will have a positive 14 nanocoulombs, and the other plate will have a negative 14 nanocoulombs. And again, y'all, I rounded, and that's okay. You could have put 14.16 nanocoulombs or 14.2. Okay, we're dealing with a really small number here, so we're allowed to round here a little bit. Okay, all right. And again, you say, well, where do you get that from? Well, go back and look at your significant figures. Okay. Actually, this should have been 1.0, and that's why it's done that way. 2 sig figs, 2, 2. So actually 3 and 2 and 2. So you go with the lowest number of sig figs. Okay. That's why we said 14. But now notice that each plate, one is positive 14, the other is negative 14. You say, well, why is that? Y'all, we have to have that. Okay, or else you would not be able, if the charge was different, then you would not have conservation of charge. Okay, anytime you charge a capacitor, one side will have a positive charge and the other side will have the same amount of negative charge. Okay, because when you close the gap or when you close the circuit, then you have because look, folks, you got to have potential difference. All right. And so you can't create or destroy charge, okay? And so when you close that circuit, when you close the capacitor, okay, then you have a potential difference, okay? And the current can flow. Does everybody understand what I mean by potential difference? You got one side positive, one side negative. You know, positive goes towards negative and vice versa, okay? Okay, I hope this helps, and there will be more videos.
Thank you.